We are returning after our vacations, and I believe everybody is looking forward for starting new seminars series, or the second part of seminar series this year. So our presenter is Boris Buchmann, and Boris is now with ANU. He is an associate professor of statistics there. Boris is doing a lot of interesting things in probability and some things related also to mathematical statistics. So Boris got his PhD, and he is originally from Germany, from I believe his PhD from University of Hanover, and then he spent some time in Germany. Then I think that he was in Hong Kong for a very short period. And then we consider definitely him as a former member of our Victoria probability group, because he spent considerable time at Monash. And then he moved to Australian National University, where he is now. And Boris is well known for his results, especially about Levy processes, but also he before contributed to processes, to differential equations with, for example, some fractional properties, and to many other areas. So Boris, you are very welcome, and the screen is yours. So you can start your talk, please.
Thank you again. I hope you hear me. Maybe you can just...
Yes.
Okay. Thank you again for your kind invitation. So I just want to thank you again for inviting me. It's a great honor to open the seminar. And yeah, so the other thing I would like to do is to write down some. So this is basically a joint work. So I can say, because I'm from Hanover, so this is not a misprint, this is Hamburg. That's why I wrote always double H. So basically this is joint work with Kevin Liu, formerly ANU, and Dilip Madan, who is Maryland. Ross was retired, also ANU. Then Markus Michaelsen is also basically a student of Alex Seemeyer, and Alex Seemeyer you also know, of course, and Adam you also may know. Okay, so basically the idea is Levy processes, so there will be a talk about Levy processes and subordination, but multivariate subordination. So it will, but anyway, we start to introduce it a bit. Then we will recall traditional subordination, thus plugging processes into each other. And then we see some familiar phases, variance gamma, and then in phase maybe not so familiar, variance alpha gamma. Then we will just say that there are some problems in higher dimension with subordination, which leads to the notion of weak subordination. And then we have some more to say about weak variance alpha gamma and variance generalized gamma. So I think I turned this anyway around. Okay, so now we hope that we have to use the mouse. Okay. So Levy process, that's a reminder. So we are working in n dimensions. So, but mostly it's also 2 in the plane. And so basically we have an n-dimensional process, and starts on 0, has independent increments, but else stationary increments also. And we also assume that we have cut-log paths. So that's already all. So it's a continuous time analog, of course, of random walks. But now if you look at the distribution at a given time point, then of course the restriction is that we have infinitely divisible distributions. So what was this again? So we have a vector now, could be just a bivariate vector, maybe 2. And then we can always write it as a sum here, basically using other IRD vectors. So this restricts basically the thing for Levy processes already. We cannot use the uniform distribution, but we have already infinite divisible distributions. So once we're in the realm of infinite divisible distributions, we can always write down the Levy-Chin formula, which is basically or we can write on the characteristic function at a given t as in this form here. So basically that's the argument theta and Fourier transformation of the distribution of xt can always be written as an exponential, and then in the exponent we have t, so t always comes out linear, psi, and then this is the characteristic exponent. And the exponent has basically three major components. One is a linear thing in theta, a quadratic term is a matrix, of course, it's here my notation. So, and then, or not, I think it's, and then the other one is, this is here a compound Poisson process with jumps bigger than one. And then sometimes, but not too often in this talk anyway, we also have maybe infinite variation jump processes. And then we have to have convergence problems. So if you have finite variation, I should say, you can just forget about this term and write here larger than 0. Otherwise, we may have to compensate. Okay, so basically any Levy process is now like the Levy-Chin formula, but any Levy process can then be written also like this accordingly. So it's mu times the identity plus the bound motion now with that's basically bound motion with sigma and 0 drift. And then we have a Poisson measure going here. That's basically the compound Poisson part. And then here we have all the small jumps, say. Okay, so then again, there's this correspondence laws, infinite divisible distribution. So if I evaluate this as 1, I can't take, and then characteristic functions of infinite divisible distributions. So I can always give me mu vector sigma matrix, covariance matrix, and some Levy measure. So it also has some properties at 0 at infinity. But then we can write down these vectors, and there's a one-to-one correspondence between them. And that's what we use also later a lot. Okay, and just do here forward, because this is now the continuous time thing. Continuous process. So linear Brownian motion I took here. So I write it always like Brownian motion, like normal distribution, but Brownian motion, and dimensions. Mu would be the drift vector. Here it's Levy, and then you have a matrix, covariance matrix, and then the Levy measure is 0. Here's a null measure, but basically that's all. So here we have a sample path of a standard Brownian move. That's basically a classical example in 1 dimension. Next one, but we also need subordinators, because we want to construct variance-gamma. So we need, what is this? These are all Levy processes, n-dimensional or 1-dimensional, which basically are concentrate. So they have basically a non-negative drift here, and the Levy measure is concentrated on the non-negative cone. So basically, in other words, they're increasing. As time goes by, we have an increasing process. And so here's an example which we see also 1-dimensional only. This is gamma subordinator with parameters, certain parameters. So that's already, you see drift 0. That's for us good always, because then the formulas later also fall into together, so easier become easier. This is my Levy measure, which looks like this. And if I would compute now the basic increments, that would be gamma distributed of this kind of thing. And yeah, basically, I should say A times T is, if I evaluate it, and B is constant. So this is one of the important building blocks of our talk already, or examples. Okay, now basically the idea is, what can we do? Of course, we could take independent Levy process, stack them into components. Then we also get a new Levy process. So that's, or we can superimpose them. We will also see this later a lot. But here our main focus is to think about subordination. So subordination means we have one subordinator, which is the Levy process, now with increasing components, basically, n-dimensional. And then the other one is our subordinate. So basically an n-dimensional Levy process. So that's now a notation we use, like composition of two things. But now these are both, so we always want them to have the same dimensions so that the notation becomes simpler. So here you just take 1 and 2, stick it in together basically. So basically for each component. So now you can ask, hey, wait a minute, this is already more advanced. You should go back to the original Bochner subordination univariate. Yeah, that's true. Then we can write this also in this notation where we have, unfortunately, I didn't write it out. But we would have all the T components equal, so we have only one time change, and plug it into this multivariate thing. So we will later use also some E vector. So, but basically, another thing which is a more recent paper by 2001, Barnoff-Nielsen tells us roughly, so he tells us more, but I just boil it down to the following thing. So we can also have here plug complicated stuff together as a subordinator here, as long as the components here are independent. And of course, they have to be independent Levy processes anyway. Then this thing here, composed version, as a subordinated process, is also a Levy process. So that's basically univariate subordination versus multivariate subordination. Now here's already an example, variance-gamma. So we have a Brownian motion, drift with drift and covariance matrix sigma. And of course, all these so they're independent. And here's a standard gamma process. So both components have the same value. And this indicates that this is the subordinator. And now we plug them together. But here, this is traditional subordination. So I take the first component of my multivariate Brownian motion, plug in T, take the second one, etc., always the same T. Another shorter way is to write it just like this, composed T, but this T is univariate, and it basically runs into the into the diagonal direction E. So E basically has only unit components. So this is the variance-gamma process by definition. So in one dimension, basically goes back. This basically is kind of, we are also going into the log return fitting business, univariate. If it's multivariate, then this is already a little bit restrictive because we immediately see that if this is a continuous process. So if we jump here and then one component, so if this guy jumps here, all components jump. So basically the jump structure is rather restrictive already. So the idea is then from Semeraro and Luciano basically is to say, hey, we want to have a multivariate Brownian motion, mu, sigma. We want to have variance, we want to use multivariate subordination here, down here. But we want to use a process which is really genuinely multivariate. So we have maybe one which is decomposed like a fixed vector here, alpha, which goes into the positive cone. So if basically this process, say it's a gamma process, So if this guy jumps, then all the components of T jump, but then maybe some of the components independently, they just run on the axis, basically, on the ones S1 and S2, say, if N is 2. So we have like this picture of stuff running independently, sometimes jointly, and sometimes independently of each other. So this vector is here deterministic. Alpha 1, you can choose it here from the positive cone. So maybe you think just about 2. And then choose, but we have to be a little bit careful how we choose all the parameters. So that's why it looks a bit complicated. But if these guys are independent gamma and you add them up, basically, component-wise, you will see that they're all unit gamma basically. And that means if I look at the components of this process here, I get again the variance gamma. So it's basically marginal. The marginals again are univariate gamma. Variance gamma, sorry, variance gamma. And so, okay, now we see fits. This fit was done by Kevin Liu also. And basically this is actually the fit. Variance alpha gamma, this model is called now variance, the vector alpha. And basically we get, strangely, these are the data which look more like ellipsoidal dependent stuff. Okay, and this, what we fit here are basically circles to an ellipsoid, which is a bit strange, but that's basically maximum likelihood estimator, and similar, same thing with another method from Dilip Madan, digital moment. And then, but this is now another, so this shows you that this doesn't really work so well. Somehow this is not really capturing the dependence. But now we're just looking to the other picture and see, that looks better basically, because now we have ellipsoids here. But now what is this? That's what I explain you next. This is already the weak variance alpha gamma process, fitted with two different methods. Okay, but also so if we go basically back to traditional okay, now I just do some more theoretical examples, I think. So one is just this one here. So if you want to look at a very simple example, say we have a one-dimensional Brownian motion, and this one-dimensional Brownian motion travels, we just put it on the axis basically, diagonal. Then this is also a Brownian motion, degenerate Brownian motion, but anyway, so it's a Levy process. So it has independent stationary increments, it's even continuous. But so now if I would like to look at the multivariate, genuine, maybe deterministic subordinator, maybe this one here is the easiest T. So maps to T. So basically this one doesn't travel on the diagonal, but it along the vector 1, 2. Basically 1, 2 times T. So this is a deterministic thing, but it's still a proper subordinator. Now if I plug this vector basically into my subordinate, then I get T as a Brownian motion T2T, as I wrote it here. And you can easily work out the covariance function of this, which is this one here, S minimum to T. And this thing is not sigma squared S minimum T. So this is not good, so that's not a Brownian motion, something else. So this thing is not a Levy process. So that shows you basically, yeah, shows you that, yeah, there's something going on. Another example is here, T, I take the same example here, but change here from 2T to a, say, Poisson process. Now I would like to look what happens to the covariance between components. So it would of the subordinated process. So I would get the same here, B2T, but then subordinate, plug in the Poisson here. Now if this is small, you can work this out as T minimum, this guy here. And then this becomes T times 1 minus whatever, E minus T. But that shows we know there's something going on. So this guy is not linear. Suppose if this is a Levy process, the multivariate thing here, then this cannot be a Levy process because this must be a linear function. So because the first moments must be always linear in time, and also the basically variance, covariance stuff. So it doesn't work. So and if one here's only two-dimensional Brownian motion, but probably you can also. That's just some subordinator, and basically I want this subordinator not to degenerate, so this is more natural. And say the Y covariance is really non-zero, then essentially that's some kind of, now this one may be nice condition, but essentially going from being correlated component correlation, also dependent component, to indistinguishable time changes. So the T's are indistinguishable. That, of course, reminds us of the situation, of course, that we said already earlier here. We need independent components for the X process. So if we want to have a general T's, we better have independent X's. Otherwise, we're running out of the Levy process context. So that's basically like a little bit like a converse thing. Okay, so the next thing is I just go back and think more about what happens actually if you look at the subordinate, and I would like to evaluate it at a given time vector now. So basically I have n dimensions here and also n dimensions here, but it's a n-dimensional vector. Of course, because it's here deterministic, this vector, or I don't know, it's of course or not, but one can show that this vector is also infinitely divisible. So basically, and one can work out the, this is a characteristic function, the characteristic exponent basically as follows. So I just go here, and I also I just go here a bit to simplify the talk a bit. I just say, assume that assume this X component is 0. So maybe we have ball in motion here. Then we have basically the following. We get here a linear thing in theta. So basically, this is the outer product of T and mu component-wise. I write it down. And then the other thing is a quadratic form, theta squared basically. But now T, this is not sigma or something, but it's some kind of outer product on the covariance. And similarly, if you want to have X jump processes, also you can also do this basically, but you get other terms here. Okay, so what was it again? Yeah, one is just the product-wise component, T and U, and then this diamond shape, basically outer product. And this one, you can also write it as two matrices, Kronecker-wise outer geodesic product. So this is a minimum matrix you build with T, and then multiply it with sigma. Here, this component 1. So here it's already a bit more complicated. We get the minimum of the vector. And then if you want to look at the Levy measure, you also have to look at the order statistics, but it can be written down. And this is basically, now we can say, we can just make up some kind of stuff and say, assume we want to have something like a time change multivariate, also subordinator, and you want to have an analog of our composition. So now, so if I have 2 dimensions n, this thing, I would like to derive it sometimes in 4 dimensions. Maybe I can also just go to a picture here. There should be also a picture. Because I want, here. So basically I want to look at this smart time clock stuff and say it's pure dump. Then I always know it jumps right in here, sometimes no drift. And I also know immediately that with this jump, somehow the first component, if it's a Brownian motion, should also jump accordingly. Similar, the second component. So basically I would like, then I can track down basically the pairs here simultaneously as a driving time change and somehow conditional distributions, if you want, of the y's. That's the idea. No, and I have to find the thing again, sorry. So basically I just say, I can just write it down like this. If my 2n, but my 4-dimensional in this picture has this characteristic exponent. And then just write down what I want to to have it. And so the idea is also, if you look at, you can also do this for strong subordination, multivariate, and then you get exactly this formulas also here out. And that's also why I also looked at it like this. So another thing would be, so this is weak. So this means finite dimensional distributions on processes. And then the other thing would be, unfortunately, we can't, of course, can't have pathwise. We can only have something in the middle where the first component equals t again. So and then it can be constructed from there backward. The second component. Okay. Maybe I just want to go to the Levy measure here. So if your drift is 0 again, then many of these components become boring, but that's happened for variance gamma, because we have now gamma processes driftless subordinator, so D is gone. So the minimum, there is no Brownian component in the subordinated process either, of course. And then these guys also go away. But still, this one here is still similar. So our time, this is a time Levy measure basically. And here we have the connection to marked point processes also. So basically subordinator jumps, they mark jumps in time, multivariate. And then we can fiddle around and find in basically conditionally on these points using, for instance, the Gaussian distribution, the jumps in space. And that's why it also has to be, it must be, an n, 2n dimensional. Okay, maybe I just go here. These are these small examples. So what happens if I take t, 2t, and twice Brownian, any b, and then put it together? Then, of course, this thing here is just deterministic, and then the second Brownian motion has to be updated now. So it's not just a subordination, but in the covariance we get basically a change according to the minimum of one minimum matrix here. So the 1, 1, 1 matrix here becomes a 1, 1, 1, 2 matrix. And what happens here, so if we go to the Poisson case, same thing here, then basically this is the same as subordination. So here we can use semi-strong, because here it's interesting, here we have jumps. And then the second component runs like subordination, at least. And then the first component, we have to find a new Brownian motion, which is independent, with the same distribution. But we can write it down, basically what it is. Okay, so then one can show that exists basically also this whole thing. And so this is now a projection. This is just because I want to go to the Y component here, subordinated component. We can work it out. But anyway, I just have a look here. But you see that's basically again the same formula, just with less components. There's some changes here, I think. Yeah, here's the correction term. It is some people, but this correction term will also be 0 here if x, so if you have Brownian motion, you don't have a correction term here. And then this looks familiar then. And these are actually, if you will see that breaks down. This is again the same, really breaking down, but we will see it here. So we have two independent things. And basically what I get, I can go back in distribution, basically from weak to strong, if basically under these two things. So either the components equal all, so then we are back to the old traditional subordination, or we have independent subordinates. So then this is then, so weak subordination is basically really an extension of traditional either uni or multivariate subordination. Marginal consistency. Of course, we would like to know if we take the case component of our weakly subordinated variance gamma, is it still also variance gamma univariate? So that's also true. So if I go down to this component, of course, then this is not a misprint. So this thing here becomes just a regular subordination. So this is now basically I have to think. Yeah, this is only two components here, marginal wise. We project, we get only two processes. And of course, if you don't care about the time, then it's only one, basically, one component here. Another useful thing is a weird property, zero. So if I have a zero drift for the subordinator, then I can, and I just write down the sum of those. So I get another subordinator, zero drift, and basically the Levy measures just add up, superimposed. But if I plug this into my weak subordination, then I get also a sum. In distribution, it becomes a sum, and this sum is then also basically follows then the original t's basically before are adding up. So independent, of course, it's like a linearity in the time. Okay, I think now I just want to, maybe I just go here. I go here. Then here, so when we have another case where we can match pointwisely for all t fixed, the subordinated process is if t is some kind of monotonic subordinator. So we only have independent x and t, but now assume that t has a property that if I take differences, t1, t2, it's different process, then I get an n-dimensional process. And it is a finite variation process. But if this process is also still a subordinator, that's of course then still another subclass. So if you have such a process, then you can also match this again in distribution. And so here's another strange case, of course. It is also interesting, for instance, if you go into alpha direction, so this is deterministic, R is univariate, this is a univariate thing. So if I like to compute now this weakly subordinated object, then in distribution, it is basically also, what is this here? I forgot already. Something like, it goes out, it's only univariate process in Tor dimension. And then this guy here has to be taken out, but R stays inside. And now you see the E, somehow the E goes, the Tor is gone and the E is here. So now this R really goes into diagonal direction. So it's again, this is the left-hand side is a traditional univariately subordinated process and matches this basically. So this is also useful if we can see soon. So now I would like to say, hey, then we can take Brownian motion, forget about the T component. And we take an alpha gamma subordinator. So this was basically what we already discussed. We plug it into the Brownian motion, but now in the weak sense. That means I can go from diagonal matrices here to full covariance matrices. And then we call this a weak alpha gamma process. And since we have, and one thing is already okay, because we can project, we immediately know that, the components are variance gamma again. And then, what else? It's here actually written. But the other thing is, we also see from the formula basically, because T is driving now all the jumps. So we can say we have stuff going in the common. This was in direction of alpha, the vector fixed. and or basically along the axis independently, or that's still the same. This really goes neatly over into the weakly subordinate process. Okay, so the whatever jump measure has to what? No, this is the same. Also, now we see we would like to compute maybe something more. Now we can use some of these formulae here. So this is now the weak bound in motion, and this is my alpha subordinator, alpha gamma subordinator. And since this is a superposition of these guys here, independent, I can just pull it out basically. So this is a linear operation in distribution. Now we have n+1 processes here hanging out around. One is this one here. It is basically anyway traveling only on one axis. So we can immediately say, this must be this one here. So now it's subordinated already, traveling on the unit. This is just a unit vector actually. And then here, this one here, this is a strange ray subordination. So this travels now into some positive direction, deterministic. But we can basically take out the alpha. So now it travels in the diagonal direction as it should. This thing stays here, we date up the Brownian motion. So this is now also a nice formula. And we basically, if we look at these processes, we see immediately gamma processes here and subordinate unit stuff. So this is also a superimposition of variance gamma processes. Univariate one traveling along basically the axis, on the axis only, and then a full one that travels all over the place. And we can write down then the coordinates of the parameters of this using our auto product. So basically, now that is this one here. So this is again the plot you already saw. So again, so this alpha gamma is this process which has sometimes common jumps, maybe here actually or something. That's probably a long alpha. And then this occurs in both simultaneously. But sometimes this stuff jumps separately, also independent of each other. That is what's meant with some kind of financing idiosyncratic time, common time. So like a local clock and a global clock. Okay, now we can also work out the characteristic function from characteristic exponent, which is this one here, which is then, this is just, you can work it out, of course, also from here, because now you know it is a sum of variance gamma. We know the variance gamma stuff. We can just plug in the formulas here. And then you can work out, of course, using the moments here at time 1, mu, and this one here. And the interesting thing is now to work out the covariance, of course, between the components, say between. And this happens to be two terms. Now, one is this one here. So it's a product of the alphas of the vector there and the mu from Brownian motion. Then A, this is also from the gamma distribution. And then this is actually what happens here in the picture you will see. And then there's another one, which is here, which comes from basically the other sigma matrix Kronecker with the minimum matrix. So we get a minimum term here. So now you see also maybe because if I go back to the picture, weak subordination, now still we don't really understand it, but at least we find already that we can put here so if you have here 0, then you're left with this term here. That's all you got if you want to fit it. So basically, but in our weak subordination, we have another term here. So we can allow for arbitrary covariance, of course, here. So that means there's another thing to play around here now. So basically, at least this explains a bit why we get now ellipsoids here. So that's better. Weak variance alpha-gamma fits better than this guy here. But still, there's another question why. This is now the remainder of the talk we know about why the hell is this thing still more or less doesn't show up here. There's another term, but it happens to be nearly zero. So the mu's of the fit are more or less nearly zero, but I don't really remember the numbers, but it's basically nearly zero. So if you're seeing, if this is big, of course, then we could also have a decent covariance for the strongly subordinated process. But if this guy is already zero, then we can't really do much with it, except, and that's happened here apparently also. So the mu's are tiny, and that explains a little bit also why we don't have any correlation here. So it's just fitting some kind of circular thing. Covariance zero. And this is maybe also related to some other effect from finance, namely also, but it's a little deeper, also maybe coming from self-decomposability. So the thing is, if we will see that if we are in higher dimensions, then, was my formula again. If we have self-decomposability, if we impose this on this model here, on all of these models, then it depends. I mean, jointly, as a joint thing, then the mu's have to be zero here. So that's maybe the data here tell us, okay, we are self-decomposable, and that's why the mu is immediately zero. And we need this kind of term here. See, what is this? So yeah, my telephone is ringing. Not that one of you, isn't it? But I don't know. I have to ignore. So now, what is self-decomposability? Yeah. Maybe you can just go back. So the thing is that we also want to recover this from some other thing, because this alpha-gamma process basically a superposition. Here, somebody is calling me. Sorry, I don't know what happens. Not. Sorry, I just hope I just switch off for a second. I don't know. Okay, I'm back. Do you hear me again? Yeah.
Yes, yes.
Okay. So basically, so assume we can always think of d to be zero here. Then basically in one dimension, we have gamma. The gamma process can do, so this looks like nearly like a gamma, so the characteristic exponent of a gamma exponential, basically. Sorry, Laplace here exponent. And so we get some kind of rational thing, if you remember this, and then we have to multiply some number here still. And so if you evaluate here a direct measure into u, you see immediately this is that the gamma distribution is a Taurian subordinator. And then, of course, the generalized gamma convolution subordinators anyway. What happens if we superimpose gamma subordinators? So normally it's what I learned still myself was if we don't change the scale parameters, then we can do this because the shape parameters always will add up neatly. But Taurian said, and what happens if you don't? And okay, then we have to find some other thing. But if you basically use now different U's here and add them up in this formula, you see that it's linear here. So we can summarize all this information really into a measure. And of course, that's interesting also in the multivariate way. Because here we have, maybe we can see it here again, three subordinators. No, I can't find them anymore. Sorry, I'm always getting a little seasick from these slides. Oh, here. So inside, you remember it was just this one plus the sum of those. So that's exactly also a convolution of gamma subordinators in higher dimensions. So that's why component-wise also, of course, but also in higher dimensions. So we can summarize the alpha-gamma subordinators also like a gamma convolution subordinator. But then, of course, Torin said, why not look at the closure of the whole thing? So you take the reclosure of all of these things, and then you get view. So can not only not only finite kind of things, but it once is useful to you just to summarize this in the sum of point measures basically. But okay. And then there's also some other thing. What is it? We can also, okay, now we can say we will put this more generally and say what's the variance, generalized gamma convolution. So that's basically like variance gamma, only that we allow for all kinds of convolutions and their limits, weak limits basically. And so we can say, yeah, but of course we don't want strong subordination because we know then that sigma has to be restricted to diagonal matrices. But if we use weak subordination, we can basically match always Levy processes or this. And this is basically then like a nice thing here. So basically, if we go back, n equals 1, so basically all this stuff collapses here inside onto the diagonal. And the U measure is also concentrated on the diagonal. And actually, that's also the Grigorionis idea, actually, to look at this process there when you have strong subordination, traditional subordination. And I forgot his name. I think he just called it subordinated Gaussian processes or something. Okay. Then the other thing was paper with Ross, where we rediscovered a bit all these things again and wrote down all these formulas, which look always messy, but basically we have univariate subordinators, and then we can have the independent case here and multivariate. But as we know, if we go just to the weak subordination, we get bigger classes, and you can write it down neatly. We don't need to consider all this stuff separately. So that's another motivation to introduce this. But the other thing I learned also from this paper was that, of course, we know if we have something self-decomposable and the bounding motion is centered, then we get self-decomposability processes. So basically, maybe I don't know what this week. I can just go maybe a little further because I just want to here. So self-decomposable is like a subclass again of infinite divisible. We can self-decompose it. And we have basically this thing here and also an older one, Hall-Green. And basically one is saying that's why this problem doesn't occur in one dimension, because basically here everything is self-decomposable. But if I go up here, then sufficient condition is centered. So basically the question is then, can we say something like going from turn around the whole thing and make it also a necessary condition. And that's also what Gregorionis did for the univariate subordination, but multivariate boundary motion basically. And so he said, and basically came up with some other condition, which is a moment condition. Basically, it's with like half moments of the Torin measure. Of course, if you have a Dirac measure here for you, then that's like a zero, then nothing for free condition. So that's of course then subordinated. But basically, if you have some kind of other more interesting Torin measure, so you have like something in the closure, then of course you can have to check this. This is also only like a side condition. The side condition turns out to be a little better actually as a Gregorionis condition. So it has more severe moments here and not a half, but I forgot it actually 2 and 3 or something instead of a half. Of course, this becomes simpler. This looks nasty, but it's basically like a multivariate kind of addition here, which becomes a constant if you only go along the diagonal. Okay, so basically then, so at higher dimension, this means basically, yeah, if mu is not 0, then this whole thing is also not self-decomposable. And so if we go back again to our picture here, maybe this explains now also a bit. So if mu here is 0, okay, there's nothing here, but if you are now in the strongly subordinated case, then this should be 0. At least for the alpha gamma process, strong. So we have 0 anyway, nothing to fit. That's why it suddenly becomes like you see this picture again here. But anyway, so if we use weak subordination, still, if mu is 0, so we will have joint self-decomposability, then we still have this bit here. So this gives us still like a kind of contribution from there. And that may explain why we see also here like a better fit for weak subordination. Now I think, I just have a look whether here's anything interesting. Oh, maybe here. Unfortunately, another question sometimes I was asked, okay, if T has marginal gammas, can we go further ahead within the Torin class? Can we find other processes, subordinators, so-called subordinators, which have gamma marginals? But unfortunately, no. Basically, you get only this boring example because everything has to be a direct measure in the projection, and so you get only this alpha gamma process comes back out here also. So that's all. So that's why. So I should Markus actually Michaelsen. Also Markus here was clever. He said, let's take a tail where we have gamma marginals, but as a Levy process, we can always go to copulas, Levy copulas. So we go to the Levy measure, and we can use the copular ideas, which are time invariant, although not depend on time. So we apply it directly on the Levy measure. So you can construct a whole bunch of Levy measures, which have basically marginal gamma, basically, also gamma marginals. And of course, if I plug them into weakly subordinate bounding motion, then they all have also variance gamma margins, basically, always. And he's doing a lot on blah, blah. So that's then another thing was we started to do with Adam Lee. The other thing which is also interesting generally for the whole thing is that we can, if we go up into the other direction, dimension-wise, not also from n to n plus 1. So I look at index sets basically. Then one can easily see that the weak subordination is also generate somehow project, can be is consistent with project families, etc. So I think that's maybe also still interesting to go and basically go back, look at fields and compose infinite divisible fields. So not just with n points, but say you have an arbitrary index set. And Adam already worked on this for sequences, but also more Brownian motion based, also cylindric Brownian motion. But of course, what I also still haven't done, something alpha stable and etc. Okay, that's all I wanted to say. So firstly, thank you for your attention. And what else? Now I wanted to see whether I just wanted to basically try to find the literature. That becomes a little bit like an adventure. I like this. Yeah. Can you see it, or maybe can
Yes,
you?
yes, we
Okay.
can see.
So basically, oh no, it's too small. That's really hard for me. So here I was thinking zoom. Then we zoom in. So basically, it's Kevin Lowe and Madan. So the first page I prepare here is basically then these two theses. One is Kevin's, who is now in Washington State, but he comes back in next year. And hopefully we can do some more there. And yeah, basically his thesis is also, you can see and find on online. And then Adam Lee also, the thesis at least also there. And I misspelled University. Okay, I have to do this better. But you can also find it here. And you also what he went to Singapore. And this is probably you guys also know Alex Seemeyer, who was here also a senior lecturer, and then he was also in Western Australia, worked with Ross and me, also now in Hamburg. And this his student is Marcus. I should invite it, maybe you see here. And they have also a couple, and Marcus has two papers also. One is similar, fitting variance gamma. Also it fits basically different if you multivariate normal, then traditional multivariate variance gamma, then variance alpha gamma, then weak variance alpha gamma. While we are not doing it a bit different, we are only looking at two things with different methods, but basically similar scope. But then here he's looking also at the copular things. So if somebody's interested in copulars, you can do this. And then the other thing I just wanted to compile better also some more literature. This one here is, Kostya will remember maybe this paper here from Buchmann, Kehler, Maller, and Siemeyer, Multivariate Subordination. So this paper, if you read the other paper here, you find some of these formulas. I know this one. This one, we see, I know it looks much more elegant because we can combine these two things as one kind of object. So the formulas really look much neater. Anyway, you can look it up, then you're horrified again. Yeah, thank you again. And then here I will prepare maybe some more papers. And yeah, that's all basically I plan at the moment. So I close now also this, or I can leave it open maybe and give now back. Thank you again.
Oh, thank you, Boris. Now we have some time for questions or comments, please.
Maybe I can just show my face here again. You can, maybe I can decode this. Maybe I just stay stop the share, and at least you can see me again.
So,
okay, Andrew, you.
yes, Boris, is the financial motivation the idea that these subordinators are the number of trades in some sense, and then the components of the different shares?
Yeah, again, yeah, I think so. Yeah, they do this, like moving in different market volumes. I'm also not an expert, unfortunately, but so I can only parrot what I read there. Yeah, that's what I think. Yeah. So basically, the original variance-gamma was we had Brownian motion, and then we just said we move differently through the Brownian world using following some market activity time.
Right.
And now you can, as you say, now you can say maybe there's some global thing going on, which is basically this alpha component. And then we have smaller local market shares and moving stuff around. So that's why this becomes more complicated than more interesting, say. Yeah. I could also say that this particular process or distribution is also already known. Actually, I found it later in some ancient book. But I think the new idea from the Mararo and Luciano basically is to put it into the Brownian motion and as a use it for subordination. I think the old thing was also the idea, can we write on multivariate gamma distributions, or can we write on basically interesting multivariate distributions where the marginals are gamma? And I think that was already, people already looked at this in some other area of reliability theory. And basically, I should also put maybe the Johnson and Kotz here as a reference. Yeah, but now it's basically, I think the problem is then really if you're not, you have to do something with the component correlation. Where was this again? So if you put it into the Brownian motion, so if you want to maintain Levy process property, then you want to use really the strong subordination, you need basically uncorrelated Brownian motions, basically. That's one thing. Yeah, and then the other thing, but that's, sorry, I go back, because that's also something I don't really understand, but apparently the self-decomposability comes also in as financial application, that something has to be rescalable again in some kind of portfolio or something like this. And then suddenly the whole thing has to be self-decomposable. And that's why I think that mu, then this conflict then with my mu vector here, which also has to be zero, then it is, of course, mad. Of course, you could say maybe marginal, as on the marginal self-decomposable, then you don't have this problem maybe, but it just comes out like this. We didn't do anything. It just, well, mu was zero basically in two different methods you get always mu is tiny. And sorry, I'm talking always off the grid too much.
Boris, I have maybe, because we are running late, but a very quick question, maybe trivial one, and maybe with obvious answer, or maybe with very difficult answer. So you introduce like a new operation, a new subordinate operation, and your result is enjoying a lot of different properties. So question is this like a unique? Say, for example, is it possible to introduce another operation with all these properties, or it's just, it must be just like your construction?
Yeah, I think it must be unique. It's some kind of coming out of some conditional thing, basically. Yeah. I think that's the only way to extend it.
Mhm.
But I forgot why. I should think about this more. Yeah. Thank you.
Mhm. Okay, thank you. Okay. Mhm. If there are no other questions or comments, then let us send Boris again.
Thank you also for, again, sorry.
And I just would like to remind that now we are returning like to our normal schedule. So the next seminar is in 2 weeks, but in morning time. And
Morning.
Kostya, is it correct at 10 a.m.? Yes.
At the moment, yes.
Yeah. Okay.
Oh, that's good.
Mhm.
I might join in then also in
Yeah.
2 weeks' times again.
Mhm.
Oh, you look